In this fifth lab, the goal is to observe the motion of a stretched slinky that is dropped from rest and falls to the ground below. Then we were tasked with comparing this observation with a computational model, including the force of gravity, drag force, and tension force from the slinky to predict the motion of the slinky. We will use Newton's second law to derive some of the formulas we use in our model. Newton's second law states that the net force is equal to the mass times acceleration. Since acceleration is equal to the object's change in velocity over its change in time, we can change the net force formula to the following. Rearranging the variables and plugging in final velocity minus initial velocity, we see a velocity update formula that we can use for our slinky. The average velocity is the mathematical average of the initial and final velocity. However, in the case the net force is not constant, average velocity is equal to final velocity. Though our slinky does maintain a constant net force while it is motionless and does not maintain a constant net force when falling, we will still set average velocity equal to final velocity in both cases, for simplicity's sake in our code. Moving on, since average velocity is equal to displacement over change in time, we can rearrange and plug in final position minus initial position for displacement. Then, once we plug in final velocity minus initial velocity, we will see a position update formula that we can use in our model. Now, we know that the force of gravity, or the weight force, which is in the y direction, is equal to -1 times the mass times the standard acceleration due to Earth's gravity g. We also have the tension force acting in the opposite direction of the weight force. Drag force is a proportionality constant b times the velocity squared. In this model, net force is equal to the weight force, tension force, and drag force. We can then plug in the net force into our velocity update formula, which we can use to find the velocity, and the position update formula to find the position when the slinky is falling. We are looking at two instances within our model. When the bottom of the slinky is motionless, which means the drag force is 0, and when the slinky falls to the ground, with drag force acting against it, but with minimal tension force. We utilize Tracker to examine the video frame by frame of the falling slinky. The y-axis is positive and up, and the x-axis is positive and to the right. Let's watch the video. Moving on to the code, we first add the mass of our slinky, which we treat as a ball in our computational model. Then we add the initial position and initial velocity, which will be the initial values to update the velocity and position in the time step. The time step has been changed to this value, as that matches with the frame rate used to film the video. This is not required, but is used to make the time steps between the model and observations match, which made it easier to graph. We set the standard acceleration due to Earth's gravity to be 9.8, and our unit vector j hat, which indicates that the y-axis is positive and pointing up. A loop is then used to continually update the position for every time step, until the total time elapsed reaches 5 seconds. We also have the proportionality constant b, which we found by a method of trial and error. We try to match the final position of our computational model with the final position of our observational data. In this loop, we include the weight force, the tension force, the velocity update, and the position update formulas. This next loop, which seeks to model the slinky falling, includes the weight force, the drag force, but removes the tension force. With this, we now have our computational model. This graph now shows position as a function of time for our video analysis of the falling slinky and the computational model. We see that the model does a good job at predicting the motion of the falling slinky. From 0 to 5 seconds, the computational model shows that the slinky is not moving, which is consistent with the observational data. The reason the slinky is motionless is because the tension force of the slinky and the force of gravity are equal. After 5 seconds, the slinky stops experiencing much of the tension force and begins falling. Because the slinky is falling, it experiences a drag force. We reason that the discrepancies between the observational and computational data may have arose because of the inaccuracy in placing the point mass for each frame and tracker. There also could have been other forces, like the force of wind, considering the video was taken outside. Thank you so much for listening.